Hello! In this video, we are going to prove the following theorem. Let a and b be non-zero real numbers. Then for every integer n, ab to the power of n is equal to a to the power of n times b to the power of n. So let's remind ourselves of our definition of non-negative integer exponents. Let a be any real number. Then for each non-negative integer n, we define a to the power of n to be a real number, recursively as follows. A to the power of 0 is going to be equal to 1, and a to the power of n plus 1 is going to be equal to a to the power of n times a for every non-negative integer n. So from this definition of non-negative integer exponents, we have proven a theorem really similar to this. We proved if a and b are any real numbers, then for each non-negative integer n, ab to the power of n is equal to a to the power of n times b to the power of n. So now we're going to talk about how we will extend our definition of non-negative integer exponents to include negative integer exponents. To do that, we are going to be using the concept of the reciprocal of a non-zero real number. Now, a common notation to represent the reciprocal of a non-zero real number is with a superscript of -1. Now, because we are about to define negative integer exponents, we are about to define this notation again. So let's use a different notation for the reciprocal of a non-zero real number temporarily. We will temporarily use the notation #a to represent the reciprocal of a non-zero real number a. Now let's recall the definition of the reciprocal of a non-zero real number. Let a be a non-zero real number. Then the unique real number x with the property that a times x is equal to 1 is denoted by #a. So that is the reciprocal of a. So now, our definition of negative integer exponents will be as follows. Let a be a non-zero real number. Then for each negative integer n, we define a to the power of n to be equal to the reciprocal of a to the power of -n. So this definition makes sense. Since a is a non-zero real number, we know that the reciprocal of a is a real number. Since n is a negative integer, -n is a positive integer. And we know how to take any real number and raise it to the power of a positive integer, according to our definition of non-negative integer exponents. So this is our definition of negative integer exponents. Now we can verify from this definition that if a is a non-zero real number, then a to the power of -1 is equal to the reciprocal of a. And to see how that happens, well, according to the definition, a to the power of -1 is reciprocal of a to the power of -1. And we know negative of -1 is just 1, so this is reciprocal of a to the power of 1. And it follows you can show using the definition of non-negative integer exponents that any real number to the power of 1 is itself. If you want to explicitly show how that happens, well, we could view the power of 1 as though it's 0 plus 1, because now we're in a position to apply the recursive part of our definition, right? Taking n to be 0 in this case. This is just the reciprocal of a to the power of 0 times the reciprocal of a, but then we know any real number to the power of 0 is 1, according to our definition. So reciprocal of a to the power of 0 is 1, so this is just 1 times the reciprocal of a, which is equal to the reciprocal of a. And that's it. We see that a to the power of -1 is equal to the reciprocal of a. So this shows that we can continue using the same notation to represent the reciprocal of a non-zero real number. Right? We can represent it as a with a superscript of -1, it's the same thing as a with an integer exponent of -1. So from here, we can just say a to the power of n is equal to a to the power of -1 to the negative n. We can interpret a to the power of -1 as a with an integer exponent of -1, or we can interpret it as the reciprocal of a. It's the same thing. So that's pretty much it. Now, a property about reciprocals that we are going to be using is the following. Let a and b be non-zero real numbers. Then the reciprocal of a times b is equal to the reciprocal of a times the reciprocal of b. So the way that you could prove this is by first noting, since a and b are non-zero, it follows that a times b is non-zero. So then, a times b must have a reciprocal. And by definition of the reciprocal of a times b uniquely satisfies ab times the reciprocal of ab equals 1. The reciprocal of a times b is the only real number that has this property. So if we can show that reciprocal of a times reciprocal of b also has this property, then they must be equal. So if we do ab times reciprocal of a reciprocal of b, we can show that this is equal to 1. Now, the idea is, since multiplication is commutative and associative, we can move things around, group together the a and the reciprocal of a, like this, group together the b and the reciprocal of b, like this. But then, by definition of the reciprocal, a times the reciprocal of a is 1, b times the reciprocal of b is 1, and 1 times 1 is equal to 1. So now we see that the reciprocal of a times the reciprocal of b satisfies this property. It satisfies the same property as reciprocal of ab, which means they must be equal. So that's it. Now let's get into proving this theorem. So, since we're trying to prove a statement about every integer, let's give ourselves an arbitrary integer. I'll call it n. Now, if n is a non-negative integer, then according to star, we get this equality, and so we're done. So now let's consider the case where n is a negative integer. Well then, to show that this equality is true, let's write out the left-hand side. So ab is a non-zero real number, and n is a negative integer. So according to our definition of negative integer exponents, this is just the reciprocal of ab raised to the power of negative n. Now, according to star star, the reciprocal of ab is equal to the reciprocal of a times the reciprocal of b. So we really just have this guy raised to the power of negative n. But now we apply star. We're taking a to be the reciprocal of a, taking b to be the reciprocal of b, and taking capital N to be negative n. Well then in that case, this is reciprocal of a to the power of negative n times the reciprocal of b to the power of negative n. But then by our definition of negative integer exponents, a to the power of n is the first factor, b to the power of n is the second factor. Right? That is just according to our definition for negative integer exponents. And that's it. Through this chain of equalities, we've established that these guys are equal once again. So whether n is an integer greater than or equal to 0, or if n is an integer less than 0, we see that this equality is true. And so that's it. This completes the proof. And so yeah, that's pretty much it for this video.